Okay, so in this video, we're actually just going to do an example. So I've talked about, practical application in the introduction to interval estimates. The second video on the concepts of it is it's giving you the background on how and why we calculate the interval estimates, including how it's related to the sampling distribution, where we get that 95% from, all that. But now in this video, we're just going to do an example. So if someone says, hey, I want to know, how confident I can be in something and what's the interval, this is just how to do it. So we're looking at the cost of dog ownership. Super important topic, probably for a lot of people who have dogs or if you're thinking about getting one. So according to Money, the average annual cost of the first year of owning and caring for a large dog in 2017 is almost $1,500. Let me tell you something based off of my dogs that I've owned. That's I'm clearly like 15 million standard deviations away from that mean. Slight exaggeration, obviously. The Irish Red and White Setter Association of America has requested a study to estimate the annual first-year cost for this breed. So using a sample of 50 people. Based on past studies, the population standard deviation is assumed to be known with standard deviation of 255. So again, this is an example where we're looking at the population mean and we know the standard deviation of the population. So they want to know what is the margin of error at 95% confidence. And then part B, use this data set to compute the sample mean. So basically just create this 95% confidence interval. So Irish setter, if you don't know what that looks like, that's an Irish setter. Let's go to the data. So in the Excel file, Chapter 8 Practice, the tab Sigma Known Setters is the data. So here's all the data. So they asked 50 different people, the cost to own your dog in the first year for the Irish setters, and you see all these examples. So we want to create a confidence interval, that interval estimate for that. So the first thing we need to do is calculate the average, right? So the average equals average. I am hitting Control-Shift up. I'm letting go of the shift. Nope, I'm not. Sorry. You know what's really hard to do is talk while you're doing something. Hang on a second. Okay, average. You know what? I'm struggling here. Now this isn't gonna work here. And now I've lost my point. Basically what you need to do, oh goodness, let's just get out of this, is select your data. You go ahead and do that while I scramble to figure out what is going on here. Oh goodness. And you know what, when I film, my computer lags a little bit, so it's even more annoying. Equals average. I want the average up equals that. So what I was trying to say is how I select the data, because it's super annoying when you have to hold the cursor. I mean, especially if you have, like, this is only 50 observations, but if you had 200, 300, 400, 500, or 1,000, it's a little bit harder. So if you hold the Control-Shift up, and then I let go of the, I think it was the Control-Shift. Like I said, it's, it's like typing in your password. It's easy to do, but if someone said, what's your password, to think about it, it's you forget. So anyways. That's our point estimate. That's our value of our true population parameter. So that's the sample statistic, basically. That's our average, our average here. So what we want to do, right, is we are interested in, from that point estimate, right, that point estimate is creating an interval estimate. So we have to add and subtract the margin of error from that. So that point estimate, right, is just our average that we just calculated. So we know a few things. We know the standard deviation that was given to us in the problem. So I don't remember what it was, 255, I think. Yep, 255. So we know that, so it's 255, so let's plug that in there. N is our sample size. We know that's 50. So we have this information. So now, remember, we have to calculate the standard error, which is the standard deviation for the sampling distribution. And it is equal to the standard deviation of the true population divided by the square root of n. So the square root is sqrt, open close parentheses for n. So that is our standard error for the sampling distribution. The next thing we need to know, right, let's just go back and look at this equation. Right, so we have our point estimate, and we have to add and subtract the margin of error, which is equal to, right, what we just calculated, the standard error multiplied by that z-score. So we are working with 95%, so we can do this a couple ways. We can go back to this handy-dandy slide that I gave you before, and so if you're working with 95%, you know your z-score is 1.96. So you could simply just plug that in for your z-score. You could just say that, okay, well, I looked it up in the table that Kristen gave us, so I know it's 1.96. The other thing that you could do, right, is use the formula that we've used learning that we learned about in previous chapters. So norm, right, because it's a normal distribution, dot s dot inverse, and we want the probability. What probability do we want? Right, we want that alpha value, 0.025. So if you go back here, right, we're working with 95%, so alpha is 0.05. But we want alpha divided by 2 because we want the area, remember, up until the first part of the sampling distribution, right? That part, the bottom part has 0.025% of the data up until that point. So it's 0.025, so we can plug that in, and we basically get the same answer, right? 1.96 with some rounding. So we can use this to calculate the margin of error. So remember, the margin of error is equal to our z-score, right, 1.96, times by the standard error. So that's our margin of error right there. If you wanted to use the z-score that we created, you can do that too. So margin of error, right, this is the second one. You could do the z-score, right, multiplied by your standard error. Notice that it's negative. So it's negative because this z-score is negative, right? Because this 0.025, right, is to the left of the mean, so it's a negative z-score. So that's fine. It's not wrong. But what you can do is just insert into that equation that you want the absolute value, ABS, and that will give you the absolute value of it. It's not a big deal if it's plus or minus, because remember, all you're doing is you're taking the margin of error and you're adding or subtracting it from the mean. So that's what we're going to do next. We have upper, right, the upper limit, or the upper portion, if you will, of our interval estimate is going to equal our point estimate, right, plus our margin of error, right, and then our lower is going to be equal to our point estimate minus our margin of error. So that right there, that is our interval estimate, 1766 and 1907. So that's all there is to it in terms of creating the interval estimate. But the last thing we want to do is think about interpretation. What exactly does that mean? Well, basically what we're doing is we're saying that we are 95, right? Because remember, we use 95%. You can use other confidence levels such as 90%, 95, whatever, but we're using 95%. So we can say that we are 95% confident that the interval 1766 to 1907, right, did I get those right, includes the true population parameter mu, which is, remember, that's what we're interested in, right? What is the real cost for an Irish setter for owners? So another way of saying it is we're 95% confident that the first year cost for an Irish setter to have one, or for the owner, is between $1,766.16 and $1,907.52. So that's what we're interested in knowing. We want to know that, okay, how much does it cost, right? Well, we are pretty certain, 95% certain, that the true cost of having an Irish setter, the average cost of it, remember the average cost, is somewhere between this much money. So practical application is if you're thinking about getting a dog, right, especially this breed, right, remember that's the average cost of it, to have it for the first year. So think about the cost of owning a dog. That's just your first year, right? You know, every year you have additional expenses, different expenses. So, you know, good example. So I hope that makes sense in terms of thinking about that. Let's just look at the margin of error, right? this is the margin of error. So let's think about this conceptually, what the margin of error really is getting at. Like, so we know that when we create this interval estimate, we have the point estimate, and then we're adding and subtracting some error. But what does that error depend on? Well, it depends on a few things. It tells us, right, a couple things. So first of all, we have the standard error of the sampling distribution. That tells us how much error there is, right? You have some type of variability in the population parameter, but it also depends on the sample size, right? The bigger your sample size gets, the smaller your error, which makes sense, right? The more people you ask, hey, how much does it cost for your dog for the first year, right? You're going to get a more accurate representation of your population. If you only ask a couple people, right, you're not either. There's a lot of error in that. So the larger your sample size and the smaller the variability, right, the standard deviation of your population, right, this number will be smaller. So consequently, or in effect, basically, your interval estimate will get smaller. So the smaller, right, the margin of error, right, the smaller your interval estimate, which ideally is what you want. You want to be able to say, not only are we 95% certain that the true confident or the true parameter, population parameter is in there, but we also want to make it a narrow estimate. Kind of looking at the dog example here, if we can say it's between almost $1,800 and $1,900, that gives us a good idea. But what if our margin of error, we had a lot of error in it, and it was like, hey, it's somewhere between $1,000 and $2,000. Well, it's a pretty big chunk of change for people. That's a pretty big difference. So the smaller we can get our error, the smaller interval estimate, and we can give people more accurate representation of the true population parameter, which is what we want to know, right? For example, how much does it cost to have a dog in the first year? And then the second part here is our z-score. It tells us not just about the error, but how much error do we allow. So if we increase our confidence coefficient from 90% to 95 to 95%, the interval is going to get wider. Why? This is because if we want to be more confident, we have to make a wider interval, basically to cover more bases. So if I'm like, yeah, I'm 95% confident, well, I can have a wider range, a wider interval estimate, because I'm not as as confident. But if I'm like, I want to be 99% sure, well, then you know what I'm going to do to basically say that I'm more certain that the true population parameter is in there? I'm gonna increase the width of my interval. So it's kind of like if someone says like, oh, hey, I want you to be so certain about how much it's going to cost me to raise this dog. Well, to make the, if you're going to say like, I'm really sure, you can say that, well, it's probably going to cost you somewhere between $500 and $5,000, right? You could be probably pretty sure that that's how much it's going to cost them. But notice what you've done is you've created your interval estimate much wider. You've gone basically from almost $1,800 to $1,900 to $500 to $5,000. Sure, you're more confident, but that interval now is much wider. So there's a trade-off basically. So you can increase your confidence, but what happens typically is your confidence interval, right, gets wider. Your margin of error goes up. So those are just some things to think about conceptually in terms of what is your margin of error, right? Where does it come from? What is it telling you? How does the standard deviation of the true population, the sample size, and then your confidence coefficient, how do those things affect the margin of error and ultimately the interval estimate that you get?